Hello everyone, I'm Ding Hao, a PhD student from the Hong Kong Polytechnic University. Today I will introduce our paper, EmbeddX, a versatile, efficient, and scalable platform to embed both graphs and high-dimensional sparse data. Firstly, I will introduce the background and motivations behind our work. There are two prominent types of data in modern online services. The first one is high-dimensional sparse data. For example, in recommendation systems, the user and item features are usually multi-hot vectors, which can be very sparse and of high dimension. The other type of data is the graph data, and the user and item interactions can be modeled as graph, where the nodes are the entities and the edges are the interactions. At WeChat, we face the two types of data of message scale. For example, we have 2.8 billion samples of 1.6 billion feature dimension, and we have a large graph with 1.3 billion nodes with 35 billion edges. We need to efficiently process the two types of data into dense embeddings for downstream tasks. A classic way to process sparse data is to adopt deep learning models on high-dimensional sparse data. The models convert the sparse features into dense embeddings using embedding tables and polling techniques. The dense features can be further transformed into dense embeddings using MLPs. And the two types of dense embeddings can be used for recommendation, search, and CTR prediction. There are also representation learning models for graph data, such as network embedding and graph neural networks. The two types of models export the graph data and encode the structure information into the node embeddings. The node embeddings can then be used for node classification, link prediction, and fraud detection. In industry, there are systems developed for supporting deep learning models for sparse and high-dimensional data like ChartDL, NEO, and Persia. There are also systems developed for supporting graph data models like Plato, AliGraph, and Plato GL. However, these systems can only support one type of the data models, but not the both. In other words, there is a lack of industrial-level scalable frameworks to support embedding models on both high-dimensional sparse data and graph data. We face three challenges for developing such frameworks. The first challenge is how to process web scale of the two types of data for online training and online inference. The second challenge is how to efficiently store, manage, and retrieve the two types of data which have different characteristics. The last challenge is how to develop joint models to leverage both types of data for more expressive embeddings. In this work, we present EmbeddX to address the above challenges. EmbeddX is an industrial distributed learning framework that can support models for both graphs and high-dimensional sparse data. EmbeddX supports a long list of algorithms from four categories. As listed in the right table, it supports algorithms of deep learning models on high-dimensional sparse data, the network embedding models and graph neural networks for graph data. What's more, we develop joint learning models that can leverage both sparse and graph data for more expressive performance. Next, I will first introduce the architecture of EmbeddX to give an overall picture. EmbeddX consists of four layers. At the bottom is the server layer that stores the sparse and graph data, manage the model parameters, and provide operator servers for offline training and online inference. Above the server layer is the operator layer that provides parameter operators for handling sparse data and the graph operators for handling graph data. In the algorithm layer, it implements four categories of learning methods. The application layer integrates with different applications in Tencent, such as search, recommendation, advertisement, and security. Next, I will give more details on each of the layers. The server layer consists of the offline training part and online inference part. The offline training part consists of parameter servers, graph servers, and training workers. The parameter servers stores and updates the embedding tables for the sparse features and dense model parameters. The graph servers partitions large graphs and store them in a distributed manner. In a typical offline training workflow, the training workers first retrieve a batch of training samples from the data pipelines, and then it retrieves related graph data from the graph servers and parameters from the parameter servers. After having all the needed data and parameters, it performs forward and backward propagation to calculate the gradients. It then sends the gradients to the parameter servers, so the parameter servers update the parameters and uploaded the latest parameters to the online servers. The online inference part of the server layer consists of key-value stores and serving workers. We use recommendation as an example to explain the workflow. When the serving workers receive the request from the end user, it will first retrieve the needed parameters from KV stores, and then it will invoke the deployed models to make recommendations for the users. In online inference, it is crucial to make immediate response to the user request. At WeChat, we need to respond within 30 milliseconds. However, such requirements can hardly be met by graph learning models, as the graph operations like graph sampling are really time-consuming. So here we optimize the online inference part by directly using node embeddings for inference without maintaining graph servers online. Such strategy is a trade-off between online efficiency and data timeliness. As we make the node embeddings as latest as possible, the data difference can be negligible, and such strategy can make graph learning models make efficient inference and meet the requirements of our applications. In EmbeddX, we also develop other optimization techniques. For example, we develop bit-level type encoding for storing heterogeneous graphs. We store heterogeneous graphs separately. Traditionally, the heterogeneous graphs are stored using the type-specific adjacency list, and which requires extra data space for storage. And here we integrate node type into the node ID integer. For example, we use the upper 16 bits to store the node type and the lower 48 bits to store the node ID. Such strategy can save hundreds of GB and accelerate heterogeneous label sampling. Other optimizations include aggressive asynchronous communication that we use to replace the traditional synchronous communication. The new communication strategy eliminates acknowledgement step to enhance the training efficiency. Another optimization is we implement multi-threaded parameter servers to respond to parallel requests of the training workers to boost up the training efficiency. In the operator layer, we provide parameter operators for the high-dimensional sparse data. The parameter operators provide efficient access to embedding tables and support highly frequent operations on the model parameters. And the graph operators support different graph sampling strategies, and we further implement the graph sampling operators with dedicated operations. For example, we propose dynamic rejection sampling to speed up random walk sampling. In vanilla rejection-based random walk sampling, the colored bars indicate the acceptance area of each edge, and the ratio of the acceptance area determines the sampling efficiency. And to handle the case where the acceptance ratio is very low, our sampling strategy can dynamically adjust the acceptance area and increase the acceptance ratio. In the algorithm layer, apart from implementing filter models for high-dimensional sparse data and graph data, we develop joint learning model that can handle both sparse and graph data. For example, we propose GraphDeepFM that improves DeepFM by incorporating a network embedding module that can encode the graph features by leveraging user item graph. And the whole model is trained using a joint loss of CTR loss and multi-hop neighbor similarity-based loss to learn more expressive embeddings. We conduct extensive experiments to validate the effectiveness of our proposed framework and other optimizations. We use 2 production datasets and 3 public datasets. The 2 production datasets are extracted from Tencent real-world data with both high-dimensional sparse data and graph data. We use training throughput to evaluate system efficiency and use AUC and hit ratio at K to evaluate algorithm effectiveness. All the experiments are conducted on a cluster of 50 parameter servers, 50 graph servers, and 280 training workers. To evaluate the overall efficiency, we train GraphDSSM and GraphDeepFM on 2 Tencent datasets, where there are both high-dimensional sparse data and graph data. We compared EmbeddX to Tencent baseline systems without any optimizations. As we can see from the right picture, EmbeddX achieves 9 times speed up on Tencent 1 dataset and over 10 times speed up on the Tencent 2 dataset. For evaluating the aggressive asynchronous communication, we compare EmbeddX to the PS Lite. As we can see from the lower table, EmbeddX boosts the efficiency by over 6% and preserves the model accuracy. We further vary the number of threads per parameter servers to evaluate the multi-threaded parameter servers. As we increase the number of threads from 1 to 4, the training throughput continues to grow, and it achieves up to 26% efficiency boost, while the model accuracy can be maintained consistent. For evaluating dynamic injection sampling, we train Node to VEC and compare our proposed sampling strategy to the vanilla rejection sampling. As we can see from the table, our proposed strategy substantially reduces the average sampling trails, and it speeds up the sampling by up to 21 times. We evaluate our proposed joint learning models by comparing GraphDSSM to DSSM on Tencent 1 dataset and compare GraphDeepFM to DeepFM on Tencent 2 dataset. As we can see from the table, our joint learning model generally achieves better performance by employing both high-dimensional sparse data and graph data. We further conduct A/B tests on 3 representative applications in Tencent, and EmbeddX achieves better performance in different application scenarios. That's all for my talking. Thanks for your listening.